Yeah, go ahead.
What's a complex number?
I'm gonna explain that. I'm just gonna. Okay, so an imaginary number is our imaginary unit I that we're used to has the property such that I squared is -1. And so this is really weird because no real number actually has this kind of property. And so we use this number here to to solve problems oftentimes a lot easier and to kind of have a different approach to different solutions. And so, or I is the square root of -1. And so if we were to imagine our real numbers, right? All of our real numbers sit on some number line, and this are at the center is 0, and then we have 1, 2, 3, -1, -2, and so on, right? And so this is our real number line, right? And we can imagine these numbers. We can use these numbers to solve problems. And we can multiply them together. We can square them, and we will get, if we square these numbers, we'll always get a positive number. But the complex numbers are entirely different. And so the complex numbers, they actually sit on a completely different axis and a completely different dimension, perpendicular to the real axis. And so our complex axis is, our imaginary axis is very similar to our y-axis, where it's perpendicular to our x-axis. But in this case, we have real numbers and imaginary numbers. And it works the same way, except now it's scaled versions of I instead of just other numbers. And so the way we describe a point in our imaginary, our complex plane is very, very similar to the way we describe points in our our xy plane. Instead of having some point, let's say 2, 3, in the complex plane, it would be still there, but it would now be described as 2 plus 3i, as kind of an extension of a real number. And so this right here, 2 plus 3i, or any a plus bi, is a complex number, where the complex number has a real part and it has an imaginary part, and together they make up the complex number. And so we can do a lot of really cool things with these numbers. There's a lot of applications for these numbers, such as we can describe rotations in 3 dimensions using complex numbers. We can describe angles, and the list just goes on. So what can we actually do with these numbers? Well, we can add these numbers together, not like our traditional Cartesian numbers where we can't really do anything with these. All we have is just a number and it sits there, but our complex numbers, we can actually add them together. So what does it look like if we add a complex number together? So I'll give an example. So if we have, for example, we have 1, 2, I, and 2i. And so what if we were to add the point 2 plus I and 1 plus 2i together? So if we add these points together, the operation is exactly the same as adding just normal numbers together, where we combine our real parts together and our imaginary parts together. We get 3 plus 3i. And so what is the significance of this? So 3 plus 3i lies way up here. And so what is the significance of this operation? Well, this is, for those familiar with vectors, this is exactly the same as vector addition, where you're just summing up the actual coordinates of your points. And so if you were to imagine some line projected here and some line projected here, the way adding up these numbers would be is you could bring this line and project it to the end of this line, and that would get there, or you can bring this line and project it to the end of this line. And either way it works. Either way it's the same thing. But this is really cool, and it's kind of similar to the concept of vectors, but it's not that important, and there are a lot more interesting applications of complex numbers. And so what if we decide to do something completely different, right? What if we were just trying to describe rotation in 3 dimensions? So for example, if we were to take our normal xy axis, and we were to rotate some point a comma b. If we were to rotate this point a comma b 90 degrees counterclockwise, like our ending point would end up being And this kind of, you just, to show this, you just kind of have to have a piece of paper, and it's fairly simple, or you can visualize it, but it just ends up being negative b comma a. So that's our ending point if we were to rotate the point a, b counterclockwise. And then again, the same kind of the same kind of process here. This point rotated 180 degrees would be negative negative a, negative b, and then again here it would be b, negative a. And so this is kind of, that's how you would describe rotation, and that's how you would, these are just very, very generic, very, very generic rotation with any point A, B. But how do you describe rotation with complex numbers? So before we answer that question, we have to kind of experiment with what we can do with complex numbers. So for any complex number a plus bi, we've already established how we can add these. And it is important, it is significant, but it's not nearly as important as what I'm about to show here. So what if we were to multiply this number here by I? What do we get? Well, if we distribute the I, we end up getting ai plus bi squared. And if we go back to our property of I squared is -1, that just gives us negative b plus ai. And so now this is your real part, this is your imaginary part. And the really cool thing is, if we were to describe this point, if we were to describe this initial point in our normal xy plane, it would just be a comma b. And if we were to describe this point in the xy plane, it would be negative b comma a. And so what we can see here is actually what happens is, if we multiply by I, we actually rotate our number 90 degrees counterclockwise. So I'll give an example. So if we wanted to find, given a point 3,5 here, and we wanted to, see where it ends up if it rotates 90 degrees. Well, based on this rule right here, we can expect that it would rotate to -5,3. But if we were to kind of change this into a complex plane, and we were to describe this point as not 3,5 but 3 plus 5i, then if we were to multiply this by I, we would end up getting, and then we just distribute the I out, we would end up getting -5 plus 3i. And so these 2 points are the same. They both land in the same spot. There's just a different way of describing these 2 points. This one is just -5 comma 3. This is an extension of -5 and then going up 3. And this is the complex number. And so that's actually a big application of complex numbers, is you can describe rotations just by multiplying by I. And the same thing by multiplying by -I. If we were to multiply by I and it rotates 90 degrees counterclockwise, if we multiply by -I, it just rotates it 90 degrees clockwise. And so it's that concept is really, really important when it comes to describing rotations, because now what we can do is we can effectively just with a single operation rotate our point 90 degrees clockwise or 90 degrees counterclockwise. But what if we wanted to take this a step further? What if we wanted to not just find our ending point if we rotate it 90 degrees, which is actually really, really simple just to do by drawing it out. What if we wanted to find the point if we rotated it by any angle, not just 90? So let's just say 30 degrees or 45 degrees, or any angle. So for example, so if we take a look at where our points I, -1, 0 land on the plane, because we can multiply by I rotates 90 degrees counterclockwise, -I is 90 degrees clockwise, and then by -1 is 180 degrees counterclockwise or clockwise. And so all of those numbers, if we take a look at them, this is our imaginary, and this is our real, and all of these numbers, so we have I, we have 1, we have -1, -I. The cool thing is all of these numbers actually sit on the unit circle in the complex plane. So, what?
You're good.
Okay, okay. Okay. So this is kind of not as intuitive at first, because how do we know it's a circle, not a square? So I'll show in just a little bit, but all of these values that we can describe rotation with, that we can multiply a number by, and it will rotate a number a certain amount of degrees, these four numbers all lie on the unit circle. And so the answer to finding the point A comma B, and we wanted to rotate it x degrees, that answer lies with multiplication by a number sitting on the unit circle. So this number I is also just the same as 0 plus 1I, or this is just -1 plus 0I. And so these are all technically complex numbers, except the I is here is scaled by 0, or the real is just 0. So, okay. So if we take a look at our axes, right? We have our imaginary, we are real, and basically, this is the operation by multiplying by I, and then again multiplying by I, and then and so on, right? So what if I were to ask the question? What if we wanted to rotate? And I'll give an example. So what if we wanted to rotate the point 3, 5? Or, so what if we wanted to rotate the point 5 and find the exact value when it ends after rotating it 30 degrees, for example? So I'll just write this out. So we want to find the ending point after 3, 5 has been rotated 90 degrees counterclockwise. Okay, so we can find this using just real numbers, and we can find this using just trigonometric identities, but that actually is really complicated and it takes a long time. But we can actually make this way, way easier for ourselves just by using complex numbers. And so the point 3, 5 in the real plane is equivalent to saying the point 3 plus 5i in the complex plane. And so if we take a look at our previous examples where we multiplied a generic point by 0 plus 1i, or -0 plus or -1 plus 0i. These all lie on the complex, on the unit circle in the complex plane. And so what we did essentially is we multiplied it by a number, and that number was, in this case, this was 90 degrees from the x, from the real axis. Or if we multiply by -1, it'd be 180 degrees from the real axis, from our initial point. And so we can do the same thing with any angle. So for example, if we wanted to write out our unit circle, and I'm just going to give the quadrant 1 of the unit circle here. Let's say we wanted to rotate, not 90 degrees, 30 degrees counterclockwise. Let's say we wanted to rotate this 30 degrees counterclockwise. Well, what we did initially, right, was we multiplied it by 0 plus 1i, which is 90 degrees from this. So if we wanted to rotate it 30 degrees, we just simply multiply it by another complex number, where that complex number lies on the that complex number lies on the unit circle, and it has an angle from the real axis of 30 degrees exactly. And so if we just use our trigonometric identities of kind of what like the sine of 30, the cosine of 30 is, right? So the cosine of 30 is just √3/2, and the sine of 30 is just 1/2, right? And then, but this point would be √3/2 plus 1/2 I, because for any value on point on the unit circle, instead of saying cosine theta comma sine theta, our point would be cosine theta plus I sine theta. And so now we basically extended our trigonometric functions into the imaginary world. And we basically made this into a complex number rather than just a real coordinate. And so, okay, before I continue, does anyone have any questions?
No.
All right. Oh yeah, go ahead.
Well, I mean, like, what's the advantage of like having the eye to like do the rotations? Like, why can't you just remember that it's just that it just turns negative and switches?
Because I here, yeah. the I gives like the 90-degree rotation, just multiplication by I, but it's the concept that you're multiplying some numbers, some complex number, and you can extend that to any angle, not just 90 degrees.
So like, what do people use complex numbers for? Like, what do they like, calculate or whatever? Like?
So this is an example of kind of kind of a one-directional rotation. I mean, technically it's this way and this way, but a one-directional rotation which can be scaled different ways, right? We can go this way or we can go this way. But if we think about it, I'll just give an example here. So, oh yeah, go ahead.
Can you give me like a real world like example?
Yeah, that's what I'm actually, yeah. And so this is, so I'll explain this in just a little bit, but if we wanted to describe a rotation, like we can describe any three-dimensional rotation, like just say I wanted to rotate my calculator like this. We can describe any rotation by 3 unit rotations. We can describe it by this rotation, and this rotation, right? And so all of these are, these rotations actually do require, and you can describe them using linear algebra with matrices, but to make them actually really easy, you can describe them using complex
But
numbers.
what if it's an object that has like more than 3 sides that it can move and stuff? Like imagine you have like a ball or something.
Well,
like
more than 3 sides doesn't mean more than 3 dimensions, right?
You can sum up, any rotation in
because
3
you can have it
dimensions.
as somewhat multiple different
Yeah, exactly.
It's like a partial of like different movements. Or
Yeah, and this is kind of like an intro lecture to one-directional rotation, and then in the next lecture or two, I'll talk about rotation in 3 dimensions and how to describe that using complex numbers. So basically, what we did before is we multiplied our point A plus BI by the point 0 plus 1I. And then we ended up getting negative B plus AI. And when we multiply the complex numbers, we just do the exact same thing as if we were to multiply A alpha plus beta times alpha plus beta. We do the exact same thing. So now, what we're going to do is, what if we wanted, to go back to this problem here, if we wanted to rotate the point 3, 5, 30 degrees counterclockwise. Well, here we multiplied it by the number, the initial number that was on the unit circle that was 90 degrees away. But now we're going to multiply it by this number that's 30 degrees away. And so 3 plus 5i multiplied by our point here, root 3 over 2 plus 1/2 I. And so we just, we write this out and we end up getting 3 root 3 over 2 plus 3 halves I, plus 5 root 3 over 2I plus 5 halves I squared. Okay, so now what we have is, so this right here is our imaginary part. And then this right here and this right here are both real numbers because I squared is just negative 1. And so this is the same thing as saying negative 5 over 2. So if we were to finally, write this point out in just using complex numbers, right, we would have 3 root 3 over 2, right, minus 5 over 2. This is our real part. And then plus, we have 3 plus 5 root 3 over 2i. And this is our imaginary part. So basically what we did is we've done the same thing as just multiplying kind of, any additive numbers in parentheses, but now we're just extending that idea to complex numbers. And so this point right here is in the complex plane, but if we wanted to just shift this point to the real plane, it would just be 3 root 3 minus 5 over 2, comma 3 plus 5 root 3 over 2. And this is our point. This is our ending point. This is the exact coordinates of where 5, 3 would land if it was rotated 30 degrees counterclockwise. And so we can not only do this with just any point, right? We can find like the exact value of like cosine of 105 degrees or cosine of 70 or sine of 75 degrees. We can find like the exact value of trigonometric functions normally just with using our additive angle identities, but we can also do this a lot easier just using complex numbers and multiplying these numbers together. And so that's where I'm gonna wrap it up, is where we can actually, so multiplying by some complex number on the unit circle actually gives us the effect of rotating rotating our number that we're multiplying it by some theta amount of degrees from the real axis. And so complex numbers are kind of a path that we can use, an alternative path that we can use to get to very real solutions. But in order to do that, we use weird and almost, it seems impossible, properties like squaring a number and it ends up negative. And so that's, for example, and I'm gonna end with this here. So a complex number, a plus bi, right? A plus bi. We rotate it, we can describe, rotation in just one direction, right? But we described that, we said that we can, sum up any rotation by a sum of 3 unit rotations in 3 dimensions, right? We have this rotation, we have this rotation, and then we have this rotation. And so those are 3 unit rotations, and we can have different scale versions. We can go this far, and so we can just sum up all of these. But in order to do that, we actually need higher dimensions. We need more than just 2 dimensions. We actually don't even need 3 dimensions. We need 4 dimensions to describe 3-dimensional rotation. Just like here, we need 2 dimensions to describe 1-dimensional rotation. And so that's where I'm going to stop off. And this idea of kind of describing rotations in 3 dimensions, like I just talked about, using a 4-dimensional number, and we actually extend, we add more complex numbers, is the idea of a quaternion number. And so that's what I'm going to talk about next time. All right. Yeah, go ahead.
Are there like other examples of like attributes of complex numbers? Like, is it just imaginary numbers? Is it like the only imaginary numbers is just like the square root of -1, or are there other like properties that they defy? Like, do they?
Well, I think that's.
Are there like imaginary numbers that defy like another mathematical property, or is it just the square root of -1?
I'm pretty sure it's just the square root of -1. But you can have like multiple complex numbers. So a quaternion number, you don't have I, you have I, J, and K.
Yeah, you have 4, right?
Yeah, you have your real part, and then you have 3 imaginary
But
parts.
they're all basically the same number because they all have the same property. But it's just like
They're all the same number, but they're completely different axes. And so that's
how
what
would you even draw the 4-dimensional axis though?
You can't draw
So,
4
like,
dimensions.
what is
Well, okay. I'll talk about the next lecture, but yeah, okay. That was 0.
Just that 8.